let's look at this guy here. So now we got to solve a circuit problem. Okay, before we didn't have to do that. So now what you're seeing here is that this question's worded a little bit weird. So let me see if I can make this a little bit more clear. Look at the polarity of that cap. That polarity of the cap is what it is initially. Clearly the current source is going to force it in the opposite direction. Probably the better way to write this thing is to say the following thing. So what we're interested in here is we want to find this voltage right here. We want to solve for VA. And what we're seeing here is that there is an initial voltage to the cap, but what we're going to say that it is, instead of that positive 5 volts, we're going to write negative 5 volts, where now we have the regular polarity of the cap due to the current source. So note that probably would have thrown you guys off on the exam, but I won't do that to you. So that's just a funky notation here. Let's do this dude, right? Yeah. Grab this SOB by the horns. And keep pouring that stuff, that clear stuff into your water container, right? So now, what are we interested in? Let's start moving here. The switch gets thrown. Beforehand, there's no current source in the circuit. Now, there's current source that is this 1 amp. Because there was no current source prior to this, that means that IL of 0 plus had to be 0. So that's a nice initial condition. Here we go. What are we solving for? You have a choice. You can do VC or you can do IL. Now, what would I do in this scenario here? I have no idea. I would probably pick IL. Good, I did pick IL. Now, why would I want to pick IL and not VC? Because if I have VC, I automatically have to equate that voltage to that voltage. But if I look at this in the language of current, I can calculate the current across the 8 ohm resistor by the source minus the inductor. So it makes it a lot easier. Here, I got to do a whole bunch of crap right here. Right? Because that voltage, I mean, how do I know what the voltage of the inductor is? I don't. So that means here that physically, choose IL of t, not VC. Okay? Now, I guess we could calculate VC, I guess, because the current here and here have to be the same. But then I have to deal with that 4 ohm resistor. So what I would do here is that if you look at this node right here, right, that node tells me that the source has to equal the current of the 8 plus the current of the inductor, which then tells me here that the current of the 8 is then just I source minus IL. That's a number, it's 1. And then the 8 has to be 8 I8, which then makes it easier to do it that way. That's why I'm choosing the inductor current and not the capacitor. So here we go, step 1. So step 1 tells me that I'm solving for IL. So here we go. So the first thing I'm going to do here is that I'm going to get KCL. I can see that these two guys are in series, so therefore the currents must be the same. So if I look at this guy, it has to be IL has to equal IC. I bring this guy over to the other side, and then I look at the capacitor value, and I convert IC, so I get 1/20th S hat VC equals 0. That's my first equation. Then I got to go to KVL. So if I focus on KVL, that means that the only way I can do this here is that if this voltage equals the same voltages. that's what I'm going to write. So I'm going to go to KVL and it's going to say V8 has to equal V4, VC, VL. So you can see I have to deal with three terms. I have this guy, that guy, and that guy. Oops, I got two of them. Gotta make a choice, I guess. VC and VL. So let's convert these guys. So note, we already said what V8 was. I can replace V8 with the current I source minus IL. So on this side, I'm going to write 8, which will be I source minus IL. And that's where I'm coming from this guy right here. On the right-hand side, note that the 4 ohm resistor is in series with the inductor. It's also in series with the capacitor. But if I look at the current of the capacitor, then I got to bring in the S hat. Whereas if I deal with the inductor, I don't. So then, I'm going to call this guy 4IL VC. Now let's deal with the voltage of the inductor. I have what? 2. It's got to be 2 S hat IL. So let me clean it up now. I'm going to take that IL to the other side. And if I do that, note that I'm going to get 8 plus 4 gives me 12. So I'm going to get 12 IL. And then I have this guy right here, which will be 2 S hat, which will give me IL. So the first term is IL. My second term here is VC. And then my right-hand side term now is I source. But I source is just 8 times 1. So let's see. How did my algebra do? 8 plus 4, 12. 2 S hat, 2 S hat. That looks good to me. So when I look at this, I'm thinking initial conditions all the time. So I'm saying, is there a term that isolates the derivative of the inductor? And the answer is this guy right here. So right away, I need that guy right there. And I'm only calling that just to help me out with the initial conditions. Now, let's go write down this differential equation here. So here we go. So now I'm going to matrix this guy up here. I'm going to pick IL as my first term just because I wrote it first. It doesn't really matter, right? Once you use that matrix form, does the order matter? No. So I go 1. Look at my IL term here. That's got to be 12 plus 2 S hat. Now I'm going to go to my VC terms. So I got minus 120 over S hat and 1. So I get minus 20 S hat. And then this other one gives me 1. And then I get IL VC. And then I look at my sources, 0 and 8. 0 and 8. Okay? Now, let's do the matrix terms now. So with this matrix terms, look at that. I get 1 times 1. Then I get minus. That minus cancels out. So then I get 1 times 1 plus, because it's a minus minus, then I multiply these two together here. So let's look at the multiplication. Let's see if this is too big of a step. I'm going to factor a 2 out of this guy. So this guy's going to be 6 plus 1. That 2 is then going to cancel part of the 20, which will give me a 10. So then this means I'm going to get 10 S hat, 6 plus S hat. And that's that. If I look on my right side then says, since I'm solving for IL, I take this guy and I replace it with that column. So then I get 0, 8, then I get minus 20 S hat, 1. So if I look at this guy here, man, I hope this is right. It is. because this term gives me 0, right? I got 0, and then I have an operator acting on 8, which is 0, so I get 0, and why is that a good sign? Look at the circuit. Look at the circuit. At steady state, what's the current of the inductor? 0. Because the current of the inductor is 0, because the cap opens up, all of the terms on the right-hand side better be 0. So now let's clean this up. So let's see that 10, I'm going to multiply through by 10. Okay, if I multiply through by 10, I'm going to get 10. Then I got this guy here, which will give me 6s hat. And then I got this term here, which will give me s hat squared times IL equals to 0. And the good thing about this is that we now know that this guy here has a final steady state of 0. So let's do the check here. Just a small check. We see that if IL at infinity is equal to B, if I plug it into this equation here, I'm going to get 0 plus 0 plus 10B equals to 0, tells me that B is equal to 0. And if I look at the circuit check, we see here that the cap opens up. If it opens up, there's 0 current in the inductor at the final steady state. So the only current going through this circuit here is through the 8 ohm resistor right there. So that means that the voltage of 8 ohm here has to be 8 volts. That's the final steady state. But we'll worry about that in a minute. So circuit check tells us that B is also equal to 0. So it's a little bit of a comfort. Now, let's go to step 2. So step 2 here tells me I got to go determine the general response. Okay, here we go. Here's my characteristic equation. My characteristic equation says that I have s squared plus 6s plus 10 equals to 0. Do I know what this is? Can I break this down? I don't think you can break it down. If you can't break it down, then that means I'm going to, at least I can't. There might be a way of doing it, but I don't see it. Yes?
You can, you can complete the square, but
that might be too much time. Because you know what I'd have to do if I have to complete the square? I'd have to look it up online. That's what I would do. Or no, hell no. I'd do YouTube. Show me how to do it, right? Okay, so what I'm going to do here is that, look what I did. Here's the characteristic equation. So what am I doing? I'm comparing these two terms and these two terms. So if I compare these two terms here, you see that 2 alpha equals 6. That immediately tells me that alpha is equal to 3. And then the second equation says that omega squared is equal to 10, and you know that omega naught is already greater than alpha. I don't know what the square root of 10 is, but it's probably like 3.1 or something like that. Whatever this is, we definitely know that that has to be the case. If that is the case, we can immediately say that we now have underdamping. So the underdamping then says that the inductor current must be e to the minus alpha t times the quantity A1 cosine omega dt plus A2 sine omega dt. Okay, so do I know what alpha is? Yes, it's 3. So from these two terms here, I know that alpha is equal to 3, and omega d has to be what? It has to be omega squared minus alpha squared square root. So omega squared is 10. Oh, nice. Dude, that's sweet, right? We don't have to worry about some nasty number. So what am I going to do? I'm going to plug it right into here. By the way, I should have written B, but B is 0, and that's the reason why I didn't. So here I go. So then my general response is e to the minus 3t, a1 cosine t, a2 sine t. And this is IL of t. So what is my job? My job is to now go calculate A1 and A2. Okay? And that's what step 3 and 4 do. You got to do those simultaneously. So we're at step 3 now. Step 3, we want to determine the initial conditions. So let's look at the circuit at 0 minus. So at 0 minus, we already said here that this guy didn't even turn on at 0 minus. So clearly there's no current in the circuit. And then we put an inductor. Maybe we have a switch for the inductor where we just close it and then we get that voltage instantly. So we already know these conditions. They already told us for this. So we know that VC of 0 minus has to be minus 5 volts. And the inductor current, I'm sorry, I should be saying plus, has to be that. So I got these two guys instantly. Okay. So now, what's the next thing that I do? I got to go take the derivative term. So at t equal to 0 plus, what does my circuit look like? Here's what I get. I get a cap, and I have an inductor, and I have this resistor, and this resistor here. Oh, what am I doing? We don't need to do that. I was going to solve the chapter 7 problem. We go here. I go look for the term with the derivative of the inductor current. So I look at the two first order equations to see if there is SIL hat isolated. And the answer is, it is isolated. Because when I look at these two equations, this is the only equation that has the S hat term. So I'm going to write this down here. So if I look at this, it's equation 2, which we talked about here. So then it should be, so let's look at this guy. So I have 8 here. I have VC. So I'm going to bring VC to the other side. I'm going to multiply 12 times that quantity here. And then I'm going to bring that to the other side. And note that there's a 1/2 right there. So I go over here and I'm going to go S hat IL at 0 plus. So I have a 2 right here. So let's put that 2 right in front. So I got to divide by 2 for the whole expression. So I have 8 minus VC. So I go 8 minus VC. Now I've got to deal with that inductor term. So then I got 12 times IL, and I bring that over, which will be minus 12 IL of 0 plus. And that looks like this. So now I'm going to put in my values. If I put in my values here, I'm going to get what? That term's a constant, which should be 4. Then VC is going to be what? It tells me that it's minus 5, and then I get minus 12 times 0, so that term is gone. So now if I look at this guy, right, it should be getting 4 minus plus 5/2. Is that right? Is my algebra looking good? Yeah. I think so. So this should then be 13/2. Right? 13/2 amps per second S hat IL of 0 plus. So if that's the case now, I now go solve, I apply these initial conditions to the general response. So now I'm at step 4. So now I apply ICs to general response. So here I go. So I have IL of 0 plus is equal to 0. And then what do? I come in, and I'm going to put 0 to this guy right here. So if I put 0 to here, that's 1. The sine term disappears, so I'm only left with A1. So that means here that I end up with A1 equal to 0. So when I go to my equation here, you can see that this term right here is now gone. I only got to worry about this term. So what am I going to do? I'm going to cross this guy out. I don't want to carry it around with me. So now, if I look at the S hat IL 0 plus, that means I take the derivative of this guy. So it's e to the minus 3t, and then I get A2 sine omega, or A2 sine of t. So there I go. So I got to take the derivative of this guy and set it equal to 0. So using the chain rule, it's got to be what? So no, I'm going to put A2 out here. The chain rule tells me it's got to be minus 3 e to the 0 times sine of 0 gives me 0. Okay? Did I do that too fast? You know, I know this isn't the PC word, but silence means that I'm doing the right thing. Right? Okay. So now I take the derivative of the second term. The first term is e to the 0. And then I got to take the derivative of this guy. If I take the derivative of sine, I get cosine. But cosine of 0 is 1. So what is A2? So what is this equal to? A2 all by itself. And if it's equal to A2, what is this guy equal to? We said that this was 13 over 2 amps per second. So now I got my second constant. So what do I do with that second constant? I'm going to plug it into my equation here. So let's go look at the solution. Now, and I hope this agrees with my notes. You know, I don't even want to look at them anymore. So let's go do that. So let's go plug this in. So here's my solution here. So now, the complete response says that IL of t has to equal what? A2, which is what? 13.2 times e to the minus 3t sine of t. This is the solution right here to the current. So now we finally reach step 5. Right? Now we gotta solve a circuit problem. But no, we already knew about that. Like, didn't you solve that already? Isn't that what we said that we're trying to calculate this voltage here? If we're trying to calculate this voltage, you can see that we already thought our way through this thing here. So what did we say? We said that the voltage across the 8 ohm resistor had to be 8 times the current of the 8 ohm resistor. And then we said that the current of the 8 ohm resistor was the source minus the inductor. So what this means here, it has to be 8 times the quantity 1 minus IL. So if you look at this guy here, it has to be what? 8 minus, so it's got to be 13 half e to the minus 3t sine of t. Did I do something wrong? Distribute. So if I distribute the 8, that's got to be 452? 52? So there's this guy right here. So that's our problem right here. So now, if I go and I plot this guy, let's plot two things. They're probably going to look the same here. Let's plot IL of T. What is this guy oscillating about? What's the inductor current initially? 0. So what's it going to do? It's going to come in here. IL of 0 minus is 0. And then it's going to have this pulse. And then what does it do? It oscillates until it dies off. Now that makes sense. We expected underdamped along this thing. Now if I look at the circuit, why is this underdamped? Well, essentially, these two guys are essentially doing what? They're feeding off of each other. So as the current comes out of the inductor, it then gets dissipated, right? It's being dissipated by this resistor here. And as, you know, and there's going to be sort of like this fluctuation as I go through storage and through the inductor and the capacitor until it completely drains off here. But on this guy here, what's the voltage across the 8 ohm resistor initially? 0. So this guy, V8 of T, it also starts off at 0 here. Why is it 0? Because there was nothing in the circuit. And then look at T equal to 0. At T equal to 0, what happens? The voltage of this guy is where? Way the hell down here. So you could see that at T equal to 0, I'm sorry, it goes up, not down. It goes from 0 all the way up to 8. Now this is at 0. At 0 plus 0.
So like when the capacitor initial voltage is given as V5, that's saying as soon as the source turns on.
Yeah. I essentially close the switch on the cap and turn this guy on simultaneously.
Okay.
So I can't have a delay.
That resistor.
Say that again?
At the start, there's no voltage.
Yeah, there's no voltage.
Okay.
Yeah, because there's no source.
Mm-hmm.
And then what you'll see here is that this guy does what? It jumps all the way up to 8 volts. And so as it moves just a little bit off this thing, now I don't know the competing factor here, but I'm assuming that this guy's going to be small. This guy's going to be almost close to 1. So the thing that's driving this is the smallness of sine. But I'm assuming that this sine value is going to be larger than this guy here. So therefore, I'm going to get a downward pulse here. So what's going to happen? So if I look at this guy here, I would expect, I don't know where the minimum is going to come, but I would expect here that this guy's then going to go something like this. And then it's going to go to 8 volts. Now, if we had time, I wonder if I did it in my notes, I probably did here, you could go and you could actually calculate that max. And that max, how do I calculate that max for this voltage here? I go in and I take the derivative of it, set it to 0, and then I find the critical point for the time, and then I take the time and I plug it back into here. By the way, that's exactly what happens in the labs here. Hold on a second, Jeremy. Let me see if I did that. Oh, I did it. So, it looks like I might have actually gotten the right answer this time. So, you could see here that it starts off at 0, and then what I ended up doing here, it looks like I probably took the derivative of this thing. So, that's effectively what I did right there. I figured out where that thing is 0 at, or maximum, and then you can see this down pulse, and it looks like it goes down to about, what? I would think that this was why is this not? Now, okay, looks like the picture I drew was not a very good picture. Because let me show you what this picture means here. And I think we did this when we were talking about the difference between the different oscillators. So what I did here is that I ended up doing this thing here, but really what's happening, what we mean by underdamped is that there is an oscillation, and along this line here, this guy only has to cross over once. So if it comes over here, so if I was to redraw this, maybe I should have drawn it something like this.
Well, it actually is the way in the graph it's crossing it from the -5.
Say that again.
You have it saying that V5 or the V initial is -5. Is that where the cross point would be?
The kid in the problem says that B C0 minus is.
Yeah, see, that one does start it at like that.
No, I don't have an answer for you. Because that doesn't make any physical sense to me. It should have started off at 0. Right? It should have started off at 0 because
Are we assuming there's a switch in there, even though it's not saying there is one?
yeah,
That might be
because I guess that if I put this in and this switches on instantaneously, there's no current here, there's no current here, so then these guys would have the same voltage. Exactly what one of you guys were saying. So physically, that would have to be the case. So then it would do that. Yes.
My idea is that at 0 minus, there's a voltage across the cap, but there's no voltage across the resistor, there's no current, but there's also no source, so what's happening?
Yeah.
How is there no current, but there's a voltage across the 8 ohms?
Probably just.
So picture-wise, this is what I would look at. Where's that thing at?
You just plug in a fully charged capacitor into a circuit at that moment.
But then there would be,
So let's look at this here. So if I was to try to draw this thing here, I essentially have it open. And this is my cap here, and then I have a switch. And then here I have a current source, but I can't really have a switch for a current source because how do I stop current from flowing, right? So essentially this guy, I'm essentially turning this guy on at t equal to 0, and then I'm closing this guy at t equal to 0. Now, what I failed to see here, right now here, is that at that instant, right, we're talking 0 plus some delta term that's tiny, tiny, tiny. There can't be any current here, there can't be any current here, and there can't be any current here. But there can be a voltage across these guys. And if there's a voltage across these guys, then they gotta have, there's a voltage instantly. Yes?
Can't the current across the resistor change instantaneously? Like, why is there no current?
Sure, and that's because the voltage is changing instantaneously.
There's no current.
Yeah, no, but the current is easier to measure, the change in that current is easier to measure.